Okay, good end of the week coming. So today is the last day of lecture of the week. It's the last new content we're going to see before we prepare for and take an exam. So tomorrow's class, we're going to be doing a full review based on the study guide. So please come prepared with questions. If there aren't any questions, I don't know what we're going to do. But I want to make sure that you have the ability to get your questions answered before taking an exam that will take Friday morning. Drop dead first assignment due date is tonight. I'm going to give the second assignment to you at some point today so that you can start working on that. And I think that's just about everything. Any questions on the schedule? Plan is for that assignment to be probably next week. All right. Last time we were in the middle of the last example I have prepared of a pumping lemma, but I actually want to go through what that full proof process would look like for this problem because these are a little bit difficult to write. So we had started thinking about the problem and we came up with a good choice for a string. So whenever we see any pumping lemma problem like this, the first step is to find that string, some string that is in the language that's going to be a good choice that allows us to split it up into cases, pump those cases, and find a counterexample for each one of those with the number of loops that you would run through, given any possible loop design that would allow us to show that some result of that is not in the language that is defined here. So the language is AB to the N, A to the K. And if we choose AB to the M plus 1, A to the M, this is going to be an excellent choice for us to be able to show this for any case. And the reasoning behind that is that the way that I'm envisioning this, there are 4 cases to this problem of where Y could come from. We know that X and Y, the getting to the loop and iterating the loop, have to come from the first M characters of the string. So if we say this is AB to the M plus 1, there are more A's and B's than M of them, and M characters. So we know that the Y for this has to be some sliding window within some A's and B's repeated, which gives us 4 cases. Y can either start with an A and end with an A, can start with an A and end with a B, start with a B and end with an A, and start with a B and end with a B. So what we need to do is split. Now that we have these 4 cases, we need to prove for each one of those cases that for any DFA within this, that we can pump this some number of times, and that pump results in a string that is not in the language. How would we proceed with the starts with an A, ends with an A, or starts with a B, ends with a B cases? What's the logic there? We went over this at the end of last class, but let's recap that and make sure we're all on the same page.
If you pump them more than once or twice, doesn't it break the pattern of A, B?
Yeah. So in order for it to start with an A, either X is empty or X ends with a B. So we can say that X either is empty or ends with a B. And then if we start with an A, end with an A, we know that Y in this case, Y is going to start with an A, doesn't really matter, end with an A. And if we repeat Y another time, so we have Y, which we know if that's X, Y squared, Z, which has to be allowed in the language. We repeat that. And these could be the same A because starting with an A and ending with an A, there could just be a single A there. But you can repeat this now before we go into Z, that is the rest of the string. And what we see here are consecutive A's followed by at least one B. We know that there's either a B here or there's a B here. So this is not part of this a to the k, this is somewhere in this portion of the string. So if this is the case, then these back-to-back a's are not allowed, and we've generated a string portion that is not in this language. Again, this is not deep enough to be a mathematical proof, but I'm also not teaching this course quite at the level of where I expect full math proofs. If you have an intuitive argument and can express that intuitive argument mathematically in a way that is not wrong, I will count it. So an argument like this is valid to me, as long as you explain that there has to be a b here somewhere. And it's very similar for the starts with a b, ends with a b case. Either x can't be empty at this point, it has to end with an a. There's no way to start this string with a b. So x is non-empty and ends with an a. So in the starts with a b, ends with a b case, we know that x is going to have something and end with an a. That something could be empty, but we do exactly the same thing here, where now we document a y starting with a b, ending with a b, document another y starting with a b and ending with a b. And we see that with these back-to-back b's, there's nothing in this language definition that allows for that. So we've created a string that is not in the language by pumping this DFA. Basically, what we've said as we do this is that there is some start state. By some process, we reach some kind of loop. This doesn't have to be a self loop of some kind. This can be an arbitrary sized loop. And from the end of that, we get to an accepting state. And all we've said is, here is the logic for what happens if we repeat this loop twice instead of once. And if we do this, that is a legal path from the starting state of this DFA to here, looping back to here, looping back to here, going to a final state. This DFA would accept that string. If this DFA exists and can handle these cases, then it needs to be able to produce these strings with these subcomponents. Since neither of these subcomponents can be part of this string, then this DFA cannot exist. But we need to show it for every possible breakdown of these cases. Because this choice for y, we don't know how the DFA is designed. If any one of these four cases is true, then a DFA type exists that would be able to handle this kind of string. So all we've said is that these two classes of DFAs can't exist. There are four classes of DFAs that we could construct, where the loop starts with an A, ends with an A, starts with an A, ends with a B, starts with a B, ends with an A, starts with a B, ends with a B. That's just saying these are the bounds of the characters that are starting and ending this loop. Does that make sense? So since we've shown it for two, we have to show it for the other two. Thoughts on how to do this for starting with an A, ending with a B, starting with a B, ending with an A? Now we need to take something else into consideration, because if we start with an A, end with a B, and duplicate it, we're still in this language, at least the part of it that says AB to the N. So what do we need to attach ourselves to now to be able to show that when we pump this some number of times, this is wrong?
Something. N is less than K.
Yeah, we need to break this N is greater than K. So we can attach ourselves to every part of this language definition. And the entire reason that we selected m+1 and m here, putting them right next to each other, is because by pumping down, setting I to 0 and not doing this loop at all, because x, y, z does this loop once, x, z without the y does this loop 0 times. So if we have some AB some number of times, and we state that, okay, starting with an A and ending with a B, that means that Y is at least some portion of this. It could be more than that. It could be all of this. We don't necessarily know, but it involves at least one AB. That's going to be the verbal argument that you would put forth, that Y must consist now to start with an A and end with a B, it involves at least one of these ABs. So if the string AB to the N, A to the K, or AB to the M plus one, A to the M is this string, and Y must be at least one of these ABs, what you're doing is you're turning AB to the M plus one, A to the M into AB to the M plus one minus some variable we haven't used yet. Doesn't really matter what you use, P, A to the K, such that P is greater than or equal to one. And if you state this, we're subtracting at least one from this, which is breaking the condition and is greater than K. Because N, you do a substitution of N for M plus one minus P, where P is greater than or equal to one, and you now have a bound on this that says that N cannot be larger than K. And the reason we can state that is that N was one larger than K to start with our example. So as soon as you remove at least one, you break that strictly greater than assumption. Do people see that? Does that require more explanation? How we doing with that concept?
I think so. I mean, it's the same as pumping down, right?
Yes. Yeah.
Not repeat that pattern. And if we remove even one set of ABs, then we're no longer, N is no longer greater than K necessarily.
Yeah.
Right? Yeah.
Yeah. So this P is just the number of ABs that Y happens to contain. We know that it has to be at least one, but it could be more than that. So you can't just put a one here, but you could say it's a worst case. It's something that's greater than or equal to one, which is why we variabilize that.
Okay. Yeah, that I got lost when it came to P. I didn't know what P was.
Yeah.
But now, okay, so P is the number
The number of ABs that Y contains.
captures. Okay.
Yeah,
Okay.
which we know has to be greater than or equal to one, because in this case, Y starts with an A and ends with a B.
Yeah.
And it's gonna be exactly the same with starts with a B and ends with an A. Except it's a little bit harder to formulate that because you're not taking out chunks of ABs, you're taking out the last bit of one chunk all the way up to the first bit of another. So you need an additional piece of an argument there that says that it's the equivalent of taking out one more than the partials.
Because if you do it with a sequence of BAs, isn't technically your last A coming from the A to the K?
It could.
Oh, it could. Oh, it could. Okay.
Well, actually, it can't, for the reason of the amount of ABs is raised to the M plus one. So the first M characters is only going to be halfway into the ABs and not all the way into the ABs. So in some situations that may be the case, but you actually don't have to account for that in this case.
Okay.
Yeah, it's weird, huh? But this allows us now to have some case, some argument for each one of these four cases, which are the only four ways that we could create this loop in a DFA. So we took this problem, we split it down into now, all right, what does player one, if we're thinking about this in terms of a game, what power do they have in terms of that breakdown X, Y, Z? So from player two's perspective in the game, we need to consider every possible route to victory that player one might have. They might come back and give us a breakdown of X, Y, Z where Y does any of these. And this is now the plan for how we are going to force player one's hand and win the game over player one, regardless of what breakdown they give us. So kind of a conditional plan of how to respond to any of player one's shenanigans. So oftentimes you'll see this in pumping lemma proofs where when the power returns to player two, You have to think about what is everything that player one could have done. Break that into cases such that no matter what player one does, there's a bin of an argument that is sitting there waiting for you that you construct for how to win the game. Have you ever played such a boring and difficult game? Games are designed to be fun and accessible, not boring and difficult.
You played forehand backhand,
Played what?
forehand backhand,
Working back.
forehand backhand. All you do is slap the other guy. That's it. That's
I've never played that. Like, how do you get to the cases? Like, if it had, say, ABC.
Yeah, you have to think about, given that and the breakdown, what are all of the different ways that
Just that we can start events.
potentially, depending on if that's the loop parameters, so that's usually the case of where the loop starts and ends in this case, but we will find more difficult breakdowns when we talk about an extended version of this later on in the course. This is the most difficult thing, I think, because when I talk about that difficult extension to this, you will have this as a baseline. Coming up with all of this for the first time, I still think might be the most challenging part of this class. If you can learn and understand how to create and deliver these kinds of proofs, then you're in a very good spot. There are more difficult things to come, but they will rely on this information and extend it. So if you understand this, then the extension is not quite the same reach that learning this for the first time is. That's just what I've seen historically.
for each case, it's an arbitrary length loop. So whatever between A and like the first and last character, it's kind of arbitrary.
Yeah, and it turns out to not matter. Because what breaks it is the fact that when we duplicate that A, whatever's in the middle A, it creates the AA. And as soon as
And
you
we're
have
breaking
that,
pattern.
yeah, you just say that for any I greater than or equal to, or greater than one, then you have to have at least one of those AA segments inside of your AB to the N.
Right.
And AB to the N cannot have an AA inside of it.
Couldn't you also do the same thing by saying that I is zero in this case, because then you wouldn't have A to A back, but then you would force
Right.
A to have B to B back to each other.
Yes.
Okay.
Yep, that would be another way you could do it. How are we doing? Does that make sense? There are frequently lots of different paths through this. If you took out an AB or starting with an A, ending with an A, then even if that did hold to AB to the N, you would be taking out at least one of those, and that would break the N is greater than K as well. So you could reasonably come up with that kind of argument as well. I just wanted to showcase a few different paths through what you could attach yourselves to in this to make an argument. So these problems on homeworks are going to be long. You will need to start with something like let L equal or assume this language is regular. If it's regular, then a DFA can be made for it. Assuming that a DFA can be made for it, and you'll just continue until you reach that contradiction. Since L is infinite and a DFA can be made for it, we can break it down into X, Y, Z, where Y is the loop in the DFA. The length of XY has to be less than or equal to M, and the length of Y has to be greater than or equal to 1. And then you will proceed by cases to show that here are all the ways that we could break down XY. And here is a counterexample for each one of those, pumping I to some value that's not 1, creating a string that is not in the language. Once you've exhaustively done that for every case, then you can conclude that no such DFA can exist. Contradiction found. The only conclusion from there is that L is not regular. So that's going to be the outline that I'm looking for in a full homework style proof. If you don't have a history of that, feel free to come talk to me in office hours and I can help you lay out one.
Will we ever have any problems of like, here's a language, prove that it is either regular or not regular?
Yes.
Okay, nice.
And by proving it's regular, we just need to construct a DFA or an NFA that works.
Yep.
Proving it's not regular can include.
Yes, so that's the easy path where you should start for any of those problems is, can I construct a DFA? If you try to proceed with a proof by contradiction, a pumping lemma for a problem that's actually regular, you will find that you cannot complete it. And I've actually seen this in students for which a question is, one of those questions does have an answer of the language is regular, and they're trying to make a pumping lemma for it, and they're trying to ask, why isn't this working? Or where do I proceed from here? And the answer is you can't. And the reason you can't is because it's regular.
So it's kind of, I guess, proving that it's regular or not regular, the process will terminate if you can do it in either direction.
Yes.
It won't if you can't.
Although what I've also seen is that people will make up steps or try to force the pumping lemma to work to show that something is not regular when it actually is regular. And I think you can learn a lot from that process if you end up down that to say, what assumption did you make that's not true? It's like those posts out there that you can create 1 + 1 = 3
Oh, yeah.
by dividing by 0 or some other mathematical operation that's not allowed. It just doesn't look like you're dividing by 0, but because it can be 0, you can prove really weird things. And again, if you don't use logic and something that is mathematically allowed, when you do this, you can create false statements out of true statements.
Well, if you had a language, I know a good baseline for seeing if it's like regular or not is if you need memory to do it.
Yeah,
But if, say, M and those two M's were different and there wasn't any stipulation about what they were, then that would be regular. But if there was a stipulation, we could prove that it wasn't. So I'm making sense.
yeah, if the N and it's, yeah, if the N and K weren't conditioned in any sense, where we just, N could be K, N could be different from K, we don't care, as soon as we don't need to count. We just need to see the structure. There are some A's and B's and A's and B's and A's and B's, and eventually we just see A's, that's regular. Yeah, it is the N is greater than K, and K is greater than or equal to 0, that is making this not regular. That's a good point, really good to see as well. Do we feel a little bit better about the process, or do we feel worse now that we've seen a more complicated example of it? I can see both ways.
Yeah, I understand it, I don't think I do. So.
Articulating it's probably the hardest part.
Yeah,
I'm full of boundless confidence, but I'm sure once I actually have to do a problem on my own.
it's funny how that works.
Yeah.
It's something to learn about humanity, because I think we all experience that. You see it, you're like, yeah, I can reproduce that. You got to reproduce it. Oh, shit.
It's like, I could go to an art museum, I could do that.
Yeah.
Yeah.
Or like the first time learning how to program and you like watch the tutorial, like, oh, that looks easy. And then you go to actually write the code and nothing works. I don't understand what's going on.
Yeah, yeah. Especially as computer scientists, a feeling we're all too familiar with.
Yeah.
And yet we still never learn from. We still have that boundless confidence every time we see something new or something. There's something to be said about the fallibility of humanity, just solely as using that as an example. So to me, it seems like hopefully you know enough to be able to get started and get stuck somewhere. This is where the office hours usually start to ramp up significantly in this class. I am all here for that. As I mentioned on the first day, I love office hours interactions. I expect that people are utilizing them when they do get stuck. Don't just get stuck and try to get out of that without utilizing everything that is at your disposal. If I get too overwhelmed in office hours, there is some overlap with the TA's office hours, and he is excellent at explaining these kinds of things. I trust him a lot for that. So I will make myself as available as I possibly can be to help with that. And if I can't, I will send you his way. And I have a lot of faith in his ability to help you as well. Anything else we need from the board? Everyone have what they need? All right, we'll move on. So yes. Let's talk about common pitfalls. There are quite a few common pitfalls in pumping lemma proofs. So if you find yourself doing some of these things, they're not great. I didn't get it, did I? All right, the first thing I see that I don't think is on this slide is instantiating M. In a pumping lemma proof, you need to make a general argument based on M and carry M all the way through your argument. At no point should you be using constants. Unless you are instantiating I. You can say for I equals 2, whenever there exists on the predicate logic for something, you can just provide an example. Whenever there is a for all, there needs to be some variable that you use for that. So if you're using predicate logic and you say for all M, there is no DFA of M size, then you cannot say let M equal 7 and proceed. And again, that just shows that there is no 7-state DFA for this problem. It doesn't say anything about DFAs of any other size. So yes, trying to use the pumping lemma to show a language is regular. There's nothing that says that if you cannot construct a pumping lemma proof, that the language must be regular. Don't go down that road. Even if you show that no string in L can ever be pumped out, if you manage to show that, we cannot use that. So the only one purpose of this disgusting process is to prove that a language is not regular. That's the only time you want to use it. Another thing, if you start with a string that's not in the language, the original language that is displayed. So in the last example, if you said let W equal, and you said something that was not AB to the M, A to the, or N, AB to the N, A to the K. Adhering to N is greater than K, and K is greater than or equal to 0. If you came up with something that was not in that language, then said let W equal that. Again, no conclusions can be drawn. A tricky example to this would be something like L is A to the N such that N is a prime number. What would your W be for such a language if you wanted to show that that language is not regular?
Just W or WWW. One is prime, right?
So if you say something like W equals A to the M, why can't that be used? Yeah, there's no guarantee that M is prime. There are instantiations of M that are not prime, and you have not created a conditional on that forces it to be prime. So M may not be prime. Instead, you need something that is defined to be greater than M and prime. So you could say, let W be A to the M plus K, where K is defined to be whatever it needs to be to create the next prime from M. Lots of assumptions about the associated XYZ decomposition. Same example as above. Given M, let W equal A to the K such that K is odd. If we subtract an odd number of A's from a prime number, it means that XC has an even number of A's and cannot be prime. That seems like it might follow logically. What are some issues?
K, an odd number isn't necessarily prime.
Correct.
And since player one also gets to choose the decomposition, they could have like 2 A's inside. With value that repeats. So then the number of A's subtracted could be even.
So can't make an assumption like K is odd. 2 is prime and even. But not all odd numbers are also prime. But every other prime number will be odd. So could you split it into cases and try to prove something for 2, and then for, assuming that every other number is odd, every prime number is odd? I still would not recommend that path. There is a better way to do this, and you will actually be working with prime numbers a little bit on one of your homework problems. So start thinking about them. They will soon be in your dreams.
Yay.
But yeah, those are frequent. Instantiating M, especially if you're trying to play the game and show that you're playing the game. I'm trying really hard this quarter to differentiate what you want to approach and how you want to think about the game. But I've historically found that someone still misinterprets me and tries to instantiate M or tries to play the game once rather than proving that player 1 cannot win the game. So that's everything for now on the pumping level. We will actually come back to it as a way to also show that a language is not in the next class of language we're going to talk about. And we will extend the pumping lemma to be able to show that it can be used again in a more complicated form to show that a language is not in that class. But by then you'll have had a good bit more experience with the pumping lemma. So hopefully it's a little bit easier at that point. As you get started on homeworks and as I start to meet with people and get a sense of what people are struggling with, I may come back to this and say, let's get some more examples and draw out some more proofs, especially ahead of the next exam where this will be on that exam. Again, this is not on the exam Friday. So there is time to learn this. But we're going to move into the next class of languages and spend quite a bit of time talking about them, because this is, I hesitate to say the most important class of language, but it's probably the most important class of language to compilers. So we've seen that we can use the pumping lemma to show that a language is not regular. Why are languages that aren't regular interesting? And the answer to that is there are quite a few constructs in programming that cannot be mapped to regular languages, but we need to be able to map in order to write programs that function. So for instance, we showed that A to the N, B to the N is not regular, right? In order to do this, we need to know how many A's there were so that we can map it to the same number of B's, which requires us to count the number of A's that we see. As soon as we have to count the number of A's, we need more than a finite amount of memory. Even if you think, well, I can instantiate a variable and keep track in that variable, there's always overflow. If you declare an integer and you count high enough, that integer can't store that information anymore. So this will never work in general, regardless of whether you make a big int with an arbitrary amount of memory. I can always create an A to the N, B to the N with an N that's just larger than that big int can store. And that becomes the counterexample for you can't create this as a regular language. Regardless of how much memory you dedicate to storing that, there's still an N that is larger than that. That is the beauty and the curse of infinity. So now imagine replacing your A's with open curly braces and your B's with closed curly braces. What are we representing in this case?
Nested curly braces.
Yeah, nested scope. So you might have a loop inside a loop inside a loop, and inside of that you have a conditional, and inside of that you have a loop, and inside of that you have a conditional. Yes, terrible code that needs to be decomposed better, but the idea of scopes inside of scope mapped to this kind of A to the N, B to the N language, where we have the start and end of a scope, and then we can define scopes recursively inside of that scope. So it seemed like we're just playing around with random languages with A's and B's in it for fun. They map to programmatic constructs that we use all the time. So nesting control structures, if statements, loops, functions, recursion, any of that can now be modeled with just this concept of A to the n, B to the n. Now, note that this doesn't allow for sequential anything within an associated scope, because we have to be able to close something before we open something within a nested structure. But we will talk about that language and how that language also is irregular, and it's just a modification of this one. So if we want to be able to reason about scopes and control structures, then we need something that allows for that. And if we just allow for regular languages, we have no hope for a compiler to be able to map scopes or understand whether a program is well formed syntactically with regards to scope. So it's something we could not account for. So we will learn about context-free languages and be able to map constructs like this with this language class. All right. Restrictions placed on a regular grammar, what were they?
Be right or left linear, right?
Yes.
And that has to do with where you place all of the non-term.
Single non-terminal. We could have an arbitrary number of terminals, but as soon as we had a variable, and we had one variable allowed, either always at the rightmost side or always at the leftmost side. So context-free is a larger class of languages. There are more languages that are context-free than were regular, and in fact, every regular language is also context-free. We'll show that later as well. But yes, every regular language is also context-free, so every language we have seen, we can define within this context. But there are additional languages that the pumping lemma could show wasn't regular that we will also be able to show within these rules as well. So many context-free languages that are not regular. A to the n, B to the n is an example of that. So we're going to relax that regular grammar restriction. And now this is very similar to the grammar problems on your first homework, where you could have non-terminals, any number of them, and terminals that appear on the right-hand side in just about any order. So here is an example context-free grammar. Go ahead and analyze it and think about some possible strings that could be produced by it. And then think about what language it represents. Yeah,
Or a palindrome of some kind, an even length palindrome.
even length palindrome, great. We had a name for that when we saw it last time, that was WWR. Is that what this language is? We have an assertion that this is WWR. Anyone else buy that or see some example, counterexample to that? That's exactly right. If you were analyzing an even length palindrome, how would you determine that it is an even length palindrome? Snap the first two characters, so the last two characters, the first and last, and then move inward. Second and second last, move inward, third and third last. And as long as that last comparison they don't overlap onto the same character, then you'd have an even length palindrome. This is kind of the rules of how you would do that in a language that only allows for A and B. You would say, are the first and last characters both A's? Are the first and last characters both B's? And then you would recurse in the middle of that string. So the non-terminal being in the middle of this is really just representing recursion. That the structure of this is defined from the outermost characters inward, recursing after we either allow for the start and end characters to be A's or B's, recurse inward. A's or B's, inward. A's or B's, inward. So yeah, string followed by the same string in reverse. Could we do this with a regular grammar?
No.
Why not? What about this language makes it really hard to either recurse just at the end or just at the beginning? We have to recurse in the middle.
Because of the symmetry.
Yeah, there's no way to tell how long the string is, and this doesn't place any restriction on how long it is, it just defines the structure of it. As soon as we have to parse it from left to right, we have to store the characters that we see so that we can map them at the end. If we allow that recursing to happen in the middle, we are making a statement that says what happens at the beginning and the end. We don't have to count one to map it to the other. We're going to map it in a single step and then recurse in the middle. And it turns out with a finite list of grammar productions, we can make rules for an infinite length string. Or an arbitrarily long string. We can use a finite amount of memory to represent structure that could be arbitrarily large in size. That's the better way to say that. All right, knowing that you can do whatever you want now, non-terminals can appear on the right-hand side in any order and anything, then come up with a grammar for a to the n, b to the m, such that n is not equal to m. What would that look like? Go ahead and toss your brains at each other and see if you can come up with a solution.
Hey.
It's not even. It's actually quite.
I don't know if there's no. I don't know if there's legit.
I'm not doing it. Wait, how you doing?
But that seems me.
That is an example. Let's bring this into language. How could we define a grammar for every string in this length? I will give you the hint that it is possible. But note that all of the A's come before all of the B's, which is a very important restriction here.
Sorry. This one, right? Skip to that one. You need more productions, but still do it.
Can't you still produce? The logic for this is going to kind of follow what you might for programming. So think from a large scope. There are two classes that this string could fall into. What are those two classes? This language is made up of two classes of sublanguages. What are those classes?
Where A is always greater or less than the number.
Yeah, there are more A's than B's, or there are more B's than A's. That is what your initial production should do, is split into that case.
Yeah.
Then proceed where one of those cases guarantees producing more A's than B's. The other case guarantees producing more B's than A's, both adhering to this structure.
Can understand more about that. So. He said we can go to this. So.
we want more A's always. Go into the case of working, actually, this doesn't work. Okay. And that's gonna either have a and it's just best with A. Because we're gonna always have A's, B's, so if you want just one A, B's, they'll just keep. Also be. That's what it's gonna be, there's, there we have.
We don't have to worry about it going back, because it's actually not gonna step over, there's a possible route.
Is there any flaws?
I think if you, no, I think you're right, if there is a way to producing something not in the language, I think that's still.
Sometimes just that quick initial nudge of here's how to think about the problem, and then it just flows from there.
Maybe.
Oh, like, yeah,
Literally, like,
what do you mean? I can just have different entities.
Like they're all A is less than. I'm gonna see.
I find that studying this material really helps with program decomposition and how to plan, how to program.
Mhm.
So I like to teach classes when I can from that perspective of even if you don't go design a compiler after this class, because you're so inspired by this material, there's still something that's relevant to whatever it is that you do in terms of analyzing code, in terms of it's thinking about breaking down problems into smaller, more manageable pieces, which is a lot of what good code design is. Looks like we have a few people still working, so we'll give it a couple more minutes. This is the remaining 3 minutes we have.
This wouldn't accept the empty string, right? Because then it would be A to 0, B to
Right.
0.
Correct. You cannot accept the empty string. We need to make a decision in the class. Do we go over it, or do I give you the day to think about it, torture yourselves over it? Go over it?
Yeah.
All right. Here's a solution. So I like this as a logical solution because we're going to immediately break this down into the more A's case or the more B's case. The S1 here is just going to recursively produce A's and B's at each end, an equal number of them, and also allow us to terminate at any point. So this guarantees that we adhere to there are the same number of A's as B's coming from S1. But what the A and the B are doing is they force at least one more A or at least one more B. And the way we're going to do that is by saying this can produce one A or more than one A, looping until we decide we're done, this is the last A we're going to have. And so there's no path through this. We have an arbitrary number of A's and B's, followed by some more A's than B's. Arbitrary number of A's and B's, more B's than A's. And that breaks down and logically works. But it's a little more complicated than necessary because that just allows for more A's. almost exactly the same thing. I don't know what that's for, actually. So, yeah, I like the solution on the left.
You said the one on the right is not for.
Yeah, that only allows for more A's than B's. I actually don't remember why that's there. It's exactly the same thing, except it's just the left-hand side of it. So if we just restricted this to more A's than B's, then that would get you there. But I don't have anything on the slide that would remind me why I put that there. So we're out of time for the day. We'll come back and continue talking about context-free languages and what we can do with them, because the answer is a surprising amount. It turns out that this class of languages helps us do the entire parsing step of compilers. The tokenizing step is going to be related to regular languages. The parsing step is going to be related to context-free languages. And with a lot of these background ideas, we'll actually be able to talk about the steps of constructing a compiler to recognize a language. Much more complicated language than one that involves A's and B's. One like Java or C or Python, Rust. So I'll see you tomorrow for more. Actually, I guess it's not technically more. We're gonna do a review tomorrow and we're gonna take an exam. So
exam.
yeah, we'll come back to this by the time it's out of your brain. You flushed it out with an exam. There'll be a significant recap on Monday.
I was in the Zoom call waiting to like join. I was like watching, waiting for a good time to interrupt.
I have office hours starting now because I don't have my next class on Wednesdays. So if you have any questions about homework, about the class, I'm headed right up there.